Great, thank you. And thank you to the organizers for the invitation to be here. It's always a really great meeting, lots of really nice talks and a deep dive into a really exciting field. So I'm going to talk a little bit about pyroelectrics and electrocalorics today and some of the things that we've been working on and touch a little bit on how we measure these things as well. So before I jump into that, let me acknowledge the people who actually do all of the hard and important work. So this is a picture of our group back at Berkeley. The work that you'll see today was primarily done by my now former student. He graduated just this last year, Shashir Pandya. But there's also some nice work from my current grad student, Gabe Velarde, and others as we go through. We, of course, have great collaborators around the country and around the world, and we're always thankful to those folks who help pay the bills for these kind of things. Okay, so why pyroelectric and electrocaloric effects? Well, we should start where, at an important point, we decided to go without you. Sorry, Ron. We're all kind of familiar with the Heckman diagram here and all the intricacies of the cross-coupling functions that come out of these exciting materials that we work on. And in particular on this side is where we're interested today in these electrothermal effects, pyroelectricity, electrocaloric effects, and these sorts of things. And these have been used over the years for lots of different applications. I'm showing just a few of them here. Lots of things with thermal sensing. We can convert waste heat into electrical energy with these systems, or you can run these things in reverse and get solid state cooling. Here's an example of some thermally driven electron emission systems. You can think about these. These are arrays of effectively AFM tips where we coated them with ferroelectrics and then drove them with really rapid temperature changes, and then electrons would spew out of the surface of these AFM tips of these systems. So you can do all these sorts of things. Now, if you compare what has been done in the electrothermal world to things maybe on this electromechanical effects side, what you'll find is that while there have been sustained efforts, in particular in dielectric and piezoelectric effects to understand the fundamental physics of what's going on, there's quite a bit less in the electrothermal world, and that includes a relatively poor understanding of the fundamental materials physics, what's going on, insufficient access to well-controlled materials that enable you to study these things at a fundamental level, and really there have been inadequate measurement protocols over the years that have led to kind of misleading ideas in this regard as well. So there's a lot of need for attention in this space. Now, one other thing that's motivating us, and we've done a lot of things on this pyroelectric energy conversion aspect, just to give you some sense of the scope of the problem here. This is a map showing the energy resources in the United States. So everything here on this side over here is showing the source energies that we put into the system, and then they flow through all these different systems, some used for electricity generation and various other locations where these things are used. What you see on the right-hand side here is where this energy ends up. This is the stuff that is actually used, and this is the stuff that is rejected as waste heat. That is about 68% of all the energy we put into the system on the left-hand side ends up as waste heat on the right-hand side. And if you break that down even further, the vast majority of it happens in this relatively low-quality waste heat regime, okay, below 230 degrees C. So if you have high quality heat, you can have things like Rankine cycles and thermoelectrics that are quite good at harvesting these medium and high quality waste heats, but there's relatively little that can be done with this low quality waste heat. It's a largely untapped resource, and so there's a big opportunity to both reduce carbon emissions, but also recover lots of money in doing this. And so these pyroelectric materials are important in this sense, in this low quality waste heat regime. So this is kind of a background point for us. All right, so if we're going to study pyroelectrics and electrocalorics, we need ways of measuring these sorts of things. And so what my group has focused on over the, actually probably almost 10 years at this point, we've been trying these things, is building in integrated measurement protocols and platforms. And so we're going to measure pyroelectric effects using what's called a 2 omega method, and we're going to measure electrocaloric effects using what's called a 3 omega or a 3 omega derived method. Okay, this is a measurement used in thermal transport community that we've kind of adapted for these materials. So what you ultimately do is you create little capacitor structures of your thin film materials with these integrated structures on top of them. So this is a microscope picture of these real things. If you had done thermal transport measurements, this would look a heck of a lot like a 3 omega system. We just basically stole that same idea. So you can create these device structures and then fabricate through to create these structures. And this allows us to either source It's back. What was I talking about? Yes, we can either source heat and measure the pyroelectric response, or we can apply a bias across these films and measure the temperature change in these systems. So we can create these out of the classic materials. Here's an example for just 2080 PZT on strontium titanate. These are hysteresis loops measured from these kind of devices. Everything looks pretty good. You can measure dielectric permittivity and loss as a function of frequency. Everything looks good in these devices, right? So we have these functional little device structures. Now we need to actually measure the properties of these things. So let's start with pyroelectrics. This is the measurement setup here. So same idea. We're going to put some current through this heater line here, and we're going to measure the voltage or the current that flows through the capacitor structure based on this. So we're applying a AC heating bias to the heater line. This is creating a power dissipation and an actual temperature change at 2 omega. So we apply it at omega and we get the power at 2 omega. And then using kind of established thermal models for the geometry, so we have to control the shape and size of these things a little bit, you can actually calculate very accurately the temperature oscillation inside of your ferroelectric capacitor. And then you can just measure your pyroelectric current and get your coefficients using this kind of lock-in based measurement, frequency dependent measurement. So you can do these sorts of things. So here's the temperature changes. That's the black data here. So if we do it slow, we get big temperature changes. If we do it fast, we get smaller temperature changes. This red data is the measured pyro current in the system, and here is the calculated pyro coefficient for the system. So using our technique, we've demonstrated that we can measure pyro currents as less than about 10 picoamps inside of these capacitor structures, so relatively sensitive. You can use these same techniques, same approaches to do these electrocaloric measurements in these systems. We do a little bit different now. We're applying electric field across the thickness of our capacitor, and we're using this line here as a thermometer to sense the temperature change in the capacitor structure. We measure that with a Wheatstone bridge-like setup. So here we're applying this applied field, typically some sign variation in field to the system, to the ferroelectric. We're measuring the electrocaloric power. We can actually separate the power that goes into electrocaloric cooling with joule heating from losses in these systems by locking into the different frequency dependent signals that come out of this. So there's a caloric part and a joule heating part that we can get. So you can measure these sorts of things, and depending on which one of these kind of peaks related to the frequency, you can pull out different information in the system. Here we've demonstrated that we can measure temperature changes in these capacitors down to about 2 millikelvin in these systems. So we can be pretty accurate in that regard. All right, so we have these ways of measuring it. Now, we want to measure pyroelectricity. It's what we'll focus on for most of it here today. So we should make sure we have some feeling of what can contribute to pyroelectric response overall. So we have the total response, this pyroelectric coefficient, and it can be built up of a lot of different components. So the first one is the intrinsic response. This is just the temperature dependence of the polarization in the system. We have to scale this by the fraction of the domains that are contributing in these materials. You can also have so-called extrinsic contributions. This results from the temperature driving changes in the domain structure in these materials. And so as the temperature changes and you get changes in domain structure, this can give rise to its own contribution. These two things together are typically called the primary pyroelectric response. Now, when we do this in thin films, we also have to worry about something called a secondary pyroelectric response. This is coming from the thermal expansion mismatch between the film and the substrate, which gives rise to a temperature-driven stress, which changes the polarization, which gives rise to this secondary pyroelectric response. And there's some expressions that you can see for these sorts of behaviors. So we need to know thermal expansion coefficient, mechanical stiffness and compliance sorts of things, piezoelectric coefficients. You can also have other contributions, things like tertiary effects. This is coming from inhomogeneous temperatures inside of your material. I generally try to avoid this because it's small and hard to measure, and so we purposely try to get the temperature as consistent across the thickness of the film as we can. So we have less than about 1 or 2% deviation in the temperature profile across the thickness of our films based on the device setups that we use. So we can typically ignore this. And then finally, if you do things that apply to electric field, and some of the applications do require you to change the field while you're doing this, you can have a dielectric contribution to the pyroelectric response. This comes from the fact that this electric field creates a change in the polarization, which also is a function of temperature. And so you can have this dielectric response as well. So despite knowing all of these things, there have been very few studies that directly study these effects and break them out in detail. Over the years, this is, again, there's a summary of some of the things we've been doing. We started by looking at this from a phenomenological point of view. These are just GLD type simulations, trying to figure out where the different contributions might be big in, say, PZT as a function of titanium content in these systems or strain. We did a little bit of measurements over the years on model systems where we could measure some domain structures and pull these things out, but there just aren't a lot of measurements in this regard. So we've primarily relied on modeling to predict where we get large pyroelectric coefficients, and there's very few studies that directly do this. So we needed some attention to try to address these sorts of things. So I'm going to try to show you 2 examples of how we can do this today, now that we've kind of matured a little bit in how we think about it. So the first is using our ability to create model versions of these materials as epitaxial thin films to help us have model systems to probe these kinds of effects. So if I take a look, this is for PZT, in particular on the titanium-rich side. I can look at the temperature strain phase diagram for this system. And depending on the substrate that I pick, I can end up with different kinds of domain structures in the system. So if I start with relatively large compressive strains, I can get purely C out-of-plane polarized films. If I start to reduce that compressive strain here into this middle, I can get mixtures of C and A, so out-of-plane and in-plane polarized domain structures. If I move on to the slightly tensile strain, onto the tensile strain side, I can have purely in-plane oriented, so A1, A2 kinds of structures. And actually in the middle between them, you can have a mixture of both CA and A1, A2. So you get this beautiful array of domain structures, a mixture of in-plane and out-of-plane domain variants in these systems. And so we have these very complex domain structures which we can tune with strain, and it gives us a nice way to have both quantifiable domain structures that could enable us to kind of measure these sorts of effects. So we started with a system like this, and what we wanted to do is try to understand how varying the strain state and the domain structure impacts the evolution of the pyroelectric responses in these materials. So here's just a few examples. If we start on terbium scandate substrates, that's over here at high compressive strains. We have at room temperature, and this is at 450 Kelvin. This is just an AFM image as a function of temperature. We have a C domain structure, and it stays C domain as we heat it up. If we start in the middle here, this is on gadolinium scandate in the CA phase. We go from having lots of CA, and as you heat it up, you see a reduction in the amount of A domains in the structure. And finally, if you go into this mixed phase regime where you have a mixture of CA and A1, A2, as you heat up, you see a variation in the amount of these domains as well. So we go to more A1, A2, and we lose CA fraction. So here we have a system where we have a monodomain C structure, and we have different films that have different fractions of C and A, and they vary in different ways as a function of temperature. Not surprisingly to anyone in this room, this also, changing these domain structures also changes the other properties, so you can see evolution of the polarization. As we increase the A domains, the measured out-of-plane polarization goes down, and the dielectric response goes up in these systems. So everything kind of makes sense. So we use strain to control the domain structures. We can go from monodomain to these complex multi-domain structures. The domain structures strongly impact properties like polarization and dielectric response. How do they affect pyroelectric response in these materials? And in particular, what are the domain wall structures, the domain structures contributing? So to extract these sorts of things, we do a couple of tricks. So the first thing that we can do is we can measure the pyroelectric response. So this is the pyroelectric coefficient as a function of the measurement frequency, the heating frequency of the system. So as we increase the frequency here, we can get to a regime at about a kilohertz where we can effectively turn off this secondary contribution that comes from the thermal expansion mismatch, because we're confining the heat primarily to the film, and we're not heating up the substrate any dramatic amount. So we can see then that there's a variation in the pyroelectric coefficient. It goes down and kind of levels out as we get past these values. So we can use this to extract the amount that comes from these secondary contributions. It's on the order of maybe 10–20% in a lot of these systems. We can then also do pyroelectric measurements here as a function of DC electric field in the system. So we can make these hysteresis loops that show us what's happening. So you can actually see the dielectric response in this slope that you see to the pyroelectric response here. But if you do these things at zero applied bias, you can get rid of this dielectric response as well. So if we do it at zero field and we do it at a kilohertz, we can have a nice way of measuring the total response and easily getting to what we need to know in the system. So what we can do here is measure the pyroelectric coefficient here as a function. This is of the different strain states in these materials. And we're going to use the monodomain sample to get a good measure, a reference value for the intrinsic response of this material. It has no domain structures. It's a monodomain system. And we can actually make a scaled estimate of what we expect the intrinsic response to be for all of these materials just based on the evolution of the polarization. This is probably reasonably valid because we're far away from the transition temperature in all of these materials. All right, so using that, we can make this kind of black line that you see here. This is kind of the expected intrinsic response based on the evolution of the polarization. And when we do the measurements, those are the red dots, we see that there's variations. These variations come from the extrinsic effects in these materials because we've turned off the secondary effects and we've turned off the dielectric response. So what we see is that there's some interesting behavior. As we go through the smaller compressive strains, this is positive, and it turns negative when we go into the tensile strain regime. So in the monodomain samples, we have no domains, we have zero extrinsic contribution. In compressive strain, the extrinsic responses work against the intrinsic behavior in this material. They're actually positive, where the intrinsic response is negative in nature. So this makes sense because as you heat these things up, you go to have more C phase in the system. So the system is actually rotating more polarization in the out of plane direction in these materials. So they work against each other. If you go on to the tensile side over here, as you heat this thing up, you're rotating more to be in the A phase, the in-plane polarized structure, and this gives rise to a contribution that works with the intrinsic response in these materials. So you can get an added behavior to these materials. And it can contribute up to about 30–40% of the overall pyroelectric response can come from these domain wall extrinsic contributions in these materials. So if you have these kind of domains, this ability to control the domain structure, you can see interesting evolution of these behaviors. We can see this show up a little bit more clearly, perhaps, if we look at the normalized pyroelectric coefficient. This is normalized to the room temperature response of these materials, and we look at it as a function of temperature in these materials. So if we start here, this kind of dark curve at the bottom down here is the monodomain sample, and we see that the pyroelectric coefficient goes up as the temperature goes up and approaches Tc. This is what we would classically expect to happen in the system. We see something quite similar when we go into the Ca domain structures. They vary a little bit at lower temperatures until they become purely C in nature, and once they do that, they look just like the monodomain samples, and they kind of follow up in a similar fashion. But when you look at the samples that had these mixed phase domain structures under small tensile strains in these materials, here what's happening is that the A domain fraction is going up with temperature, and this is adding this extra negative, the same sign extrinsic contribution, and that's rapidly driving these things to have a higher pyroelectric coefficient than you expect until they go through the full transition and get rid of having this change in the domain structures. Then they start to come back towards the normal behavior. Just to confirm that this was really what was happening, we double-checked this by doing some temperature-dependent X-ray studies as well. We went to APS and did some temperature-dependent studies. Here I'll just show you some examples from one of these mixed phase samples. And there are figures that have not come across in the transfer here, but there should be some very nice reciprocal space maps that you can imagine in the corner here that show exactly what I'm telling you they're doing. Oh, there they are. They've decided to come up now. All right, so what you can see here is that you get a temperature-dependent evolution of the A domain peak intensity in this system. And you can actually, if you do this appropriately, quantify this, and from the X-ray measurements, make an expectation for your domain fraction change, which almost matches within about 10% what we measured experimentally using our direct measurements as well. So, using strain and temperature, we can change how these domain structure evolve in the system, and these can significantly contribute to the pyroelectric coefficient in these materials. And this could be a very nice, promising route to change the pyroelectric response. All right, so this response is quite complex, right? There are many possible contributions. We have this very complex expression for these sorts of things. But we wanted to question whether you could figure these things out if you don't have these kind of model materials. If I can't make a monodomain version of this system, can I still separate these things out? And so to do this, let's consider a different question. Let's consider, I showed you PZT as a function of strain before with domain structures. Now let's ask the question, how does the pyroelectric responses and contributions evolve as a function of chemistry across the phase diagram, right? So as I change the zirconium content in the system. So there's a lot of work on how things like dielectric and piezoelectric effects change with chemistry. It's less so for the pyroelectrics. Now the problem for us is that we can't make monodomain versions of all these different chemistries. We don't know how to do that experimentally, and so we have to come up with other ways of sorting these things out. So if we take our expression for the total pyroelectric coefficient, we can start to break this thing down and see what we can control. So we can first get rid of the tertiary effect. Again, as I said before, we're trying to control the geometries and the temperature profile such that we typically have less than about 1% temperature variation across the thickness of these films, making the tertiary effect negligible overall. The second thing that we can work on is we can clear out these secondary effects. So we just do this as a function of temperature. And the key here is that we can model very accurately the thermal penetration depth in these systems. We can basically turn off the heating of the substrate by going to the right frequency regimes. This shows up very clearly in this in the x equals 40, 48 here. So this is right near the MPB for this system, where we see this big frequency dependence and then it levels off in this system. So if we do this for all of these different chemistries across the PZT phase diagram, we have measures anywhere from about 70 to 29 microcoulombs per meter squared per Kelvin pyroelectric coefficients. And these scale, as you would expect, directly with the magnitude of the piezoelectric coefficient. So it's biggest near the MPB, where we have the biggest strain-induced changes in polarization. So tertiary, secondary, we can take care of relatively quickly. What about the dielectric response in these materials? Well, the dielectric response shows up because if you look at the permittivity as a function of temperature and as a function of field, we have this d epsilon dt kind of behavior that we have to understand. This is changing as a function of temperature and field in these systems. So what we can do is we can measure these kinds of responses for the material and see what we get for these constants. So we measure for the different PZT compositions noted here, and you can see these are measured near the temperature regime where we're doing these measurements for the pyroelectric response. So using the same delta T window, about 19 degrees near room temperature, we can measure as a function of field the evolution of the permittivity. What we see here is that these things kind of even out by about 200-300 kilovolts per centimeter. We kind of saturate out these effects, they're suppressed, and the biggest effect is happening in the MPB composition as well. We can then take this and we can do linear fits to these locally in the system to pull out this d epsilon dt, this value that goes inside of this, these parentheses here, and we can have this value for the system, and then we can calculate the the dielectric contribution to pyroelectricity in these systems. What we see is quite interesting. So it's always 0 at the beginning, but it can get quite large in some of these systems. So near the MPB, this can be as large as about 115, 120 microcoulombs per meter squared Kelvin. That's like almost the full size of the overall pyroelectric response in these systems in the opposite direction from what you'd like it to be. So we can have big dielectric responses. All right, so we had secondary and tertiary, we took care of dielectric. What about the total and the intrinsic responses in these systems? So we can do just a good old-fashioned pyroelectric measurement of the whole thing overall to give us our total response. So this is the pyroelectric current as a function of electric field, and this is the calculated pyro coefficient as a function of electric field for the system. These measurements were done at 1 kilohertz, where we have basically turned off the secondary aspect, and we can see the switching behavior that we expect for our ferroelectric systems overall. Now, what we can do is get a little bit creative about trying to pull out the intrinsic and extrinsic responses in these materials. Now, if you think about it in dielectric materials, there have been a number of ways that people have tried to separate intrinsic and extrinsic behaviors over the years, including going to low temperatures to freeze out domain wall motion and all these sorts of things. So we actually started with that sort of measurement, but there are nonlinearities in the temperature changes that happen in the measurement setup at low temperatures that make it difficult for us to accurately pull these things out. What we did instead was to do these measurements as a function of applied field, where if we go to high enough fields, we can effectively quench out extrinsic contributions. So here's these pyroelectric coefficients measured as a function of increasing DC field in the system, such that we're only left with the intrinsic behavior in these systems. And there's a number of papers in the literature that do these sorts of things, and then you can extract back from this using a linear extrapolation method back to kind of an intrinsic zero field value for your sample in these systems. So when we do these sorts of things, what we find is that there's a relatively small E-field dependence of the intrinsic response in PZT materials. And the total and intrinsic response both decrease with decreasing titanium content, and they can be quite large. The intrinsic contribution can be quite large. It's a large fraction of what we've measured for some of these materials. Okay, so bringing it all together here, we got to get the extrinsic contribution dealt with, and then we can have a full story of what's happening. So we have this expression. The only thing that we haven't figured out here is the extrinsic contribution for these materials. And what we can do is we can solve for this in a self-consistent fashion. We've measured everything else, and we know that this extrinsic response should go to 0 as it goes to high fields. And so we solve until we get this thing to come to 0 at these high applied fields. When we do this, we did this for similar materials to the data I showed you in the first part of the talk, where we had the monodomain samples, and it matches within about 3% the final result that we got from this approach, and using the monodomain samples to check it as well. So now we have this approach to give us these sorts of behaviors, and here's the take-home message, right? So now we can look at the pyroelectric coefficient as a function of composition. This is going from titanium-rich to zirconium-rich in the system, and we've broken it out. So you see the total measurement here is this line, but then we have the intrinsic, extrinsic, secondary, and dielectric responses broken out for each one of these compositions. So the total and intrinsic responses decrease as the titanium content goes down in the systems. The extrinsic contribution has a sign reversal, okay? It changes sign. It goes from being positive at these compositions to being negative at these compositions as you cross the MPB. And the dielectric and the secondary peaks are maximized close to the MPB, where you have the largest dielectric piezoelectric responses in these materials. So all told, we can now separate out all these sorts of things. We can figure out what fractions of things are coming from intrinsic and extrinsic and secondary and dielectric and all these sorts of things in the system. If you're doing applications where you're applying a bias to the sample, one better pay attention to how large those dielectric responses can be. They can be some large fraction of the overall behavior that you have, and they're often opposite to what you want them to be. So the pyroelectric coefficient is a rather complex property, and one needs a pretty fundamental understanding of the materials and its structure to understand how this thing is evolving. All right, so what else can we do? A few words about calorics, and then I'll try to wrap up here. So we've looked using the same device. We've also measured the electrocaloric effects. So if I take those same samples from the first half, this set of PZT films that were strained at different levels, we can also measure the electrocaloric coefficient as a function of field and strain. And we can see, again, differences in the intrinsic and extrinsic responses in these materials. So here, what we're finding is that under compressive and tensile strain, respectively, we see a diminishment or enhancement of the responses overall. So slightly different behavior for electrocaloric than pyroelectric. We can also look at other types of materials. This morning we had some data of some beautiful talks about the hafnium oxide-based systems. We've also, like everybody else in the world, gotten pieces of these from the Fraunhofer Institute guys and done some measurements there. We see very similar things to what we talked about this morning. We see wake-up behavior in the pyroelectric responses. We see reasonable pyroelectric coefficients for these systems overall. One thing that was interesting here is that if you do this as a function of wake-up cycle, this is the pyro coefficient, that's the red data, we see this wakes up and comes eventually to kind of a level value. But if you measure the electrocaloric coefficient, it is consistently high across all of the measurement cycles that we do, suggesting that there might be different contributions to what's going on. It is also 4 times larger than I would expect based on the pyro coefficient in these systems. This suggests that there might be something like defect dipoles, which could be responsible for things like this pinching that you see here, giving additional configurational or dipolar entropy that could be leading to larger effects in these systems. So this is something that needs to be studied more, but points to some interesting kind of physics happening inside of these materials. All right, so with that, I should wrap up and just say I've shown you this very complex pyroelectric coefficient property today, and I've shown you kind of 2 approaches that can break it apart, right? So we can create model versions of materials to help us understand the different contributions, or we can use our measurement approaches to kind of separate out these effects in a thoughtful way. So with that, I'll thank you for your attention, and I'd be happy to answer any questions. Thanks. Oh, she's got it.
All right, do we have any questions? All right.
Well, thanks for your talk. And in terms of pyroelectricity, when the frequency of applied field is omega, the applied heat is omega, yes. The polarization responds with 2 omega, right?
Right.
And then in terms of electrocaloric effect, the story is the same, right?
Yeah, so I buzzed through it quickly, but there is a frequency dependence to the caloric power as well, right? So the power is on 2 omega. There's additionally a resonance in that system as well. So we can get the Joule heating and the electrocaloric heating are convoluted at one frequency, but you can go to higher orders and you can actually separate out these frequencies, these contributions.
So can you say that that 2 omega is a kind of second harmonic generation?
No, it's just where the power happens at, right? So for the heater line, right? So I'm driving a current through the system, and the power is just dissipated at 2 omega. That's it. It's nothing. It's no fancy, up conversion of frequencies there. It's just how the power is dissipated in the system.
Thank you.
Okay, we have time for one more.
You can ask later.
So when you report here this beautiful temperature-dependent or composition-dependent pyro effect, decompose, you are doing that at a given electric field, right? And so
yes, exactly. So this is going to vary. I think I put this in for 100 kilovolts per centimeter kind of applied fields, just as a reference frame. It's going to vary as I showed in that figure. So at 0 bias, there's none, and it peaks for each sample. It peaks at a slightly different temperature, near where it switches, of course, right, in these systems. But as you drive this thing, so depending on what kind of applied bias you have, you could have a really deleterious effect happening in your system if you're applying a bias during the measurement of these things. You just need to know that these are there. You avoid them all at 0 bias, but it is a function of field.
And the other polarization that you monitor is simply the spontaneous polarization or the remanent polarization in the loop that you calculate?
That's a good question. So we've actually done the measurements in both ways. So many of the things that I've shown you for these loops are almost quasi-static. They're very slow types of measurements. So you should think of that as almost as being at remanence in these systems. Mm-hmm. We have tried to do faster measurements. It cuts down on our on the accuracy of our pyroelectric and electrocaloric measurements to do these things faster, but it's a balance. So if you wanted to do that, I think we can think about ways of doing those experiments both on field and at remanence is relatively easy. On field's a little harder. It's a good question, though.
All right, while Nicole sets up, we'll take your question.
Do you want this too?
Oh, good question. Okay, yeah. I thought there wasn't time. So specific question and general question. So a specific one is, what was the silicon content of that Hafnia result?
Oh, geez. I don't remember.
Okay.
Not a lot.
Okay,
like
the general question is, people have talked about pyroelectricity and electrocalorics for
Yes.
a long time. So why aren't there any practical devices out there?
Where's Brendan? So right over here is Brendan, who is thought of some very exciting applications, including remote energy generation based on some of these systems. I would say that this field has historically suffered from the fact that actually measuring temperatures is very hard. And doing these things accurately has led to a huge range of reported values in the literature that has made it difficult to kind of lock in on certain things. So I would say that you can optimize the devices in 2 ways. If you have lots of waste heat to throw away, you can optimize to get power out, but the efficiency will be very low. It kind of depends on your application. If you need efficiency, then you need to do everything very slowly and the total power will go down. I think with the understanding of the materials that we have now and some of the work they've done for absorber layers and things like this, you can do a lot better than historically has been demonstrated. There are companies that have existed to try to work on these sorts of things, but it has never turned into like a real commercial application for the pyroelectrics. The European team has some beautiful data on the caloric system as well. So I think there's a concerted effort to really see what's real and what's not in this space. But why has it not turned into a full market? I don't know.
All right, let's thank Lane one more time.
Thanks.
What does this middle button do?
It allows you to move the cursor.